in this unit, we have discussed really 3 different types of functions. We have discussed our power functions, our polynomial functions, and then also our rational functions. What this last lesson kind of looks at is comparing power functions, exponential functions, and log functions. We'll look at kind of the long run, we'll look at some short run, we'll do a little bit of review on actually writing formulas for those types of functions. So just to get us started here, kind of basic review, let's get down kind of in one place the general formulas for a couple different types of functions. First, our linear function, we should all be very familiar with that. That's our basic y equals mx plus b, where we know that m is our slope, b is our y-intercept. Looking at our power function, so this is the type of function we started this current unit with. This is our y equals k times x to the p, and we know that both k and p are some constant. Now, power functions and exponential functions kind of at first glance look very similar. So in general, an exponential function is y equals a times b to the x. So if you look at this, the one main difference that you're going to see between a power function and an exponential function is where your variable is. So in an exponential function, that is where your exponent is the variable, whereas a power function, your exponent is some numeric value, okay? They both have some sort of coefficient there, some sort of base, but really notice the difference. Power function, your base is x, here x is the exponent. And then finally, our log function in general is just y equals log of x. Okay, so what we're going to look at first are just comparing our power functions kind of to one another. So what I have here is a set of power functions, and you can see that your powers increase going from 1 to 1.5 all the way up to 5. And then over here in the 2 different graphs, they're really actually the same graph. The first one is more on the long run. So this would be looking at them kind of on a zoomed out scale. And then the second one is actually, you can kind of see where this is coming from. If we take this portion of the graph and blow it up, that's what we have over here. So this would be on our short run. Alrighty, so what I want you guys to do, I want you to stop the video. I want you to take a couple of minutes. You are going to match these functions to one of the graphs in each of these. So you'll use these functions here, and then you'll also use them here. So looking now, hopefully you tried this on your own. So looking now at this first graph, we've talked about power functions. That was the first day of this unit. And we talked about how increasing the power makes that function grow quicker. So hopefully you realized, first of all, that this y equals x is going to be that linear function. And then we just move up as we increase that exponent. Looking at the second one then, it's kind of in reverse order. So first, we have that linear function, and then the exponents increase this direction. So the whole point of this and having these 2 different graphs to look at, for a power function, okay, because we're simply talking about power functions here, on the long run, which is what we're seeing here, on the long run, we would say that higher powers dominate. meaning the higher the power, the quicker it grows. Now on the short run over here, we would say that smaller powers dominate. And again, this is only on the short run. So this is only looking at that, basically this little tiny area. It's blown up over here for you. So you can see the lower the power here, the quicker that's growing. The higher the power here, it's going a little bit slower. But then once we run long, then those higher powers start to dominate. The next thing that we are looking at is comparing power and exponential functions. So again, these are the two that look kind of similar. Specifically, we are going to graph the power function y equals x to the fourth, and then we'll graph the exponential function y equals 2 to the x. So you can take a second, graph those on your calculator. Here's what we should have. So we're seeing, I graphed y equals x to the fourth here in pink. So we're seeing it kind of starts off growing quicker than the exponential, but then the exponential y equals 2 to the x, which I have here in purple, on the long run, that is going to dominate, okay? So summarizing that, any positive, we have to be a little specific here in what types of exponential and power functions we're discussing. Any positive increasing exponential, like we had here, any positive increasing exponential function will eventually grow faster than any power function, which is what we saw there. Similarly, any positive decreasing exponential will decay faster than any positive decreasing power function. Looking now at comparing log functions to power functions. So what we have, it's already graphed for you. You have a power function and you have a log function. And specifically, you have the log function, just the basic y equals log of x, that's the blue. And then we have the power function y equals x to the 1/2 in red. So what we can see here is that our power function is going to grow more rapidly than the log function. So here, any positive increasing power function eventually, it might take a while, but eventually it will grow more rapidly than both your common log function and your natural log function. Okay, so just kind of some general information about comparing these types of functions. The main thing to take away is to understand in comparing two different types of functions, for example, log and power or log and exponential, just understand what's going to grow faster, okay? And then the last thing that we're going to look at, actually not the last thing, next to last thing, is we are going to have a review on writing formulas for different types of functions. So remember that our linear function is just our y equals mx plus b. This is the form that we're going to have our formula in. Our exponential is y equals ab to the x, and then our power is the y equals kx to the p. Now, we should be pretty solid on writing linear functions. You've done that so many times for so long. And you should be pretty solid on writing the power function just because we've done that recently. The one that we might really need some review on are those exponential functions. So what I'm going to do is I am just going to give you the final formulas for the linear and power, and then I expect you guys to, on your own, go back and do the work to make sure you do, in fact, know how to do that. But we'll go through the exponential completely, okay? So like I said, for the linear function, you should end up with y equals, and you have some fractions here, 63 over 4x plus 33 over 2. And once again, I do expect you guys at this level to take the responsibility to actually go back and do the work for both A and C on your own. What you should get for C for that power function is y equals 3/4 x to the 6th, all right? So then what we are going to actually review together, because it's actually been since first semester that we did this, is we will go through the review of the exponential function. So you are given essentially two ordered pairs here. You're given -1 3/4 as one, and you are given 248 as the other ordered pair. So we're going to start with that general exponential function, y equals ab to the x, and very similar with how we do a power function, we're going to plug in our values of x and y to this formula. So first, I'll have 48 equals ab to the second, and we'll divide that by 3/4 equals ab to the -1st. So again, where I'm getting that, I'm using this general formula. I'm taking values of x and y, plugging them in, dividing that by the equation you get when you fill in the other x and y values. From here, we will divide. So first of all, a cancels out, and then 48 divided by 3/4 is 64. And then we have b to the second over b to the -1st. What that simplifies to is b to the third. So then we're just going to take the cube root here and get that our value of b is 4. And then we take that and we substitute that value of b in for either of these equations. So I'll just choose that first one. So we have 48 equals a times 4 squared, and then solve for a. 4 squared is 16, divide, and we get the a is 3. So then we take those two values, plug them in. So y equals 3 times 4 to the x would be our exponential. The very last thing that we have in here, it's really just kind of a review. We're taking the different types of functions that we've looked at, and we're just doing a little bit more practice with our long-run behavior. So the first example that we have is a rational function, and actually they're all three rational functions now that I look at it. So the first one, remember, for a rational function, the long-run behavior, we're going to look at our leading term. So this is going to, on the long run, resemble y equals 1 over x to the 6th, and we're just kind of taking those leading terms and simplifying. If you graph y equals 1 over x to the 6th, if you're not quite sure what that looks like, it's kind of something like this. You can always just plug that in your calculator, get a rough sketch here. So when it's asking for the long run behavior, basically we're looking for what happens to the function as x approaches both positive and negative infinity. These might be the same, it might be different. So here, as x approaches positive infinity, our function gets close to 0. As x approaches negative infinity, it does the same thing. So what we can say is that y approaches 0 as x approaches both positive and negative infinity. You can write that all kind of together in one statement. All right, for this next one, it's not really a rational function since it's not a polynomial on top and bottom. The best way then to look at something like this is just to look at the graph. So if you put that on your calculator, you see something that kind of looks like this when you graph it. You kind of looks like a horizontal line, kind of bumps up and then goes like that. You can zoom in a little bit and do a couple different things. Definitely looking at your table of values is going to help you. So if you look at your table of values, and if we start looking as x goes to infinity, we can see that this function is getting really close to 0. So we'll say that as x approaches infinity, y approaches 0. And then we need to make another comment, or another statement I should say, as x approaches negative infinity, because it's not actually the same. It might look like it's getting closer to 0, but it's actually not. It's kind of leveling off. And where it's leveling off, this might seem weird, but where it's leveling off is at 7/9. Now, why is that? Here's why that is. So basically, as your x values get so small, it's essentially 0. So these terms basically go away, leaving you with it approaching 7/9, okay? On the very last one, here, if we look at the numerator and the denominator, what this is going to resemble, because this leading term totally dominates that power function, this is going to resemble y equals e to the x. And the reason for that, again, is because e to the x dominates x to the 100th, okay? That exponential, remember, is going to outrun the power. So if we look at the function e to the x on our calculators, it's going to look generally, like our basic exponential, like that. So we can see that as x gets closer to infinity, so does y. And then as x approaches negative infinity, we know that our exponential is going to go to 0.